Dear friends, let's start our today's talk. Our speaker is Professor Semih Özlem, and his talk is entitled The Parity in Tensor Categories from Hexagon Counting to Virtual Nodes. Let's welcome.
Okay, let me just bring up the slides. Wait a second. Okay. All right. Hi, everyone. So I would like to today talk about parity in tensor categories and from hexagon counting to virtual knots and some potential exceptional structures. And this talk is based on also discussions with Professor Manturov and Professor Kaufman. And thanks for inviting me here and coming to listen to the talk. So first, I would like to sort of remind us what a tensor category is and how do we get these strange diagrams and how can we possibly reach a parity out of those diagrams. So a tensor category consists of a category with a bifunctor that takes a, so it's the objects of the tensor category would be mapping pairs of objects in C to an object in C through this bifunctor, and the morphisms would likewise be mapped under the bifunctor. And we have what is called an associative, instead of...
So is it my...
yes?
Yes, is it my problem with connections? Maybe mine. Yeah, excuse me.
Yes, I will come to the connections after after I go over just. So first, I will tell you a little bit about a piece in my PhD thesis where there was a discussion on these things, and then I will come to the connections. I will come to the map from the classical to virtual and parity in your setting and how it may connect to the one that I'm constructing here. So we have, instead of imposing that the product be associative or commutative, we might instead have isomorphisms that tell us how the two products are actually identified or mapped to each other. So this would be called a associativity constraint and a commutativity constraint. So just if we consider just the commutativity constraint by itself, then so if we consider, for example, let's see, is this, oh, there, okay. So if we consider four objects, W, X, Y, and Z, and consider the possible placement of parentheses around them, so I could basically do it in this fashion. But there are other placements as well that map under the associativity constraint. Shifting the inner parentheses by one, we reach at this placement, and then Z is still at the end. Or we could shift the middle one, so we would end up at W, X, and Y, and Z. And let me just this. So these are associated to each other through just one associativity condition. And then I could further shift this to W, X, Y, and Z. And in between here and there, I could do another shift in parentheses, keeping X, Y in the middle and leaving Z as the same. And this diagram So the associativity constraint coupled with the identity or appropriate coupling with other morphisms gives these morphisms in between these objects, and this forms a pentagon. So this pentagon should be commutative or commutative up to isomorphism for there to be an associativity constraint that's meaningful. But this is only for a specific ordering on the a specific sequencing on the four objects, and it doesn't entail commutativity at all. Now, when we introduce commutativity, we could then ask the question, how should the commutativity and associativity constraints fit together? And this gives another diagram. So
excuse me. My philosophy is that associativity corresponds to gamma and pentagon, and commutativity corresponds to G and K and hexagon.
Okay, that's wonderful, but I would like to know the exact details of the correspondence because it's not so clear in my mind.
Okay.
And maybe we can discuss it later, or if it's not too long, you can just go ahead and explain.
Oh, well, maybe long.
Later. Okay. So then the diagram associated this time is basically this diagram here, which let me try to make it a little bit bigger. This time, instead of four objects, we just focus on three objects. But instead of just the three objects, I focus on all the possible permutations of the three objects. And that's going to give us 3 factorial 6 possible listings, but there are 2 possible placements on those. So that gives 12 possible tensor products that could be formed out of 3 objects on only ordering and on a choice of parentheses placement on one of the 2. So the left-hand side of the diagram here lists, well, maybe not exactly, but okay, so not exactly. I wanted to say one half just corresponds to left placement and the other half corresponds to right placement, but that's not exactly true. So, and you know, it's a sort of a good exercise how you obtain this diagram, but we put all possible associativity and commutativity constraints, and we get this interesting shape. Ordinarily,
excuse me, I'm interested in which algebra structure is behind that. Maybe it can be related to octonions, various products of, yes.
Yeah, I am guessing so. So I began exploring in that direction, and I want to share some preliminary results of what I've gotten so far. So basically, normally in textbooks, you will just see the middle hexagon, and it will say, this is your coherence condition, and it suffices. But if we wanted to impose that coherence condition on all possible configurations, we actually get more hexagons into the picture, and we get sort of this more crowded looking picture if we focus on just 3 objects and possible things that could be possible tensor products that could be produced out of them. So then the next thing to consider is, well, this is basically a graph, and just a second. So this is a graph. So since I'm considering permutations of the 3 objects, well, I could just say, well, S3 obviously acts on this graph by taking each vertex to each vertex, and whenever there is a associativity constraint, whenever I rewrite these letters, the shifting in parentheses stays the same, so the edge is preserved. So S3's action on the graph, on the vertices, is actually induces an action on the graph, and similarly for commutativity constraints. So then I could consider the orbits of the vertices, the edges, and the possible two cells, the hexagons and the squares, under the action of S3. And
One more remark. There is a
Mhm.
permutahedron, there is an associahedron, and as I remember,
Yes.
the permuta-associahedron.
Yes, that's exactly right. This is the permuto-associahedron, actually, that we're looking at.
May I
Uh-huh.
may I ask a little question to you told us that you see here some you look at you look at this in like to permutate some permutations.
Mhm.
I have a question. Is it correct to see here the braids and the braids that act on some
Yes,
space of
that's a very, very nice observation. Obviously, a tensor product can be, by seeing commutativity as a crossing, can be turned into a braiding diagram. And so the braid, we could also consider the braid group acting, or the braid group's performance underneath this diagram. I did not specifically focus on that aspect in this talk, but it's definitely worth exploring, and it would be a very nice addition. So that's very nice observation. So let me continue. Oh, let's see, where's the... So basically, if we focus a little bit in further detail, so I colored this diagram. So the blue edges are actually the associativity edges, and then the commutativity edges are of two types when we look into them. So in one of them, I'm going to call the red ones inner commutativity. So that means that I have a product, say x, y, tensored together, tensored with z, and then I just permute x and y, the inner product elements together. And then that would give me yx tensor z. So there is between 1a and 3a in this diagram right here, there's a red edge, as you can see. On the other hand, I also have what I called orange, but to make it a little bit more visible, I actually drew it in green. The green edges are outer commutativity edges. So, for example, let's pick the one between 3a and 6b. So this time, y tensor x tensored with z, I permute the y tensor x as a single object with z. And then I obtain z tensor y tensor x, which is the object in 6b. So I'm going to call those outer commutativity. So this basically colors and classifies these nicely. And then in this diagram, I'm going to try to basically consider the question of how do I get various two cells, or the hexagons. I'm going to yes.
Okay, is it okay? I have another stupid question, but as I see, you consider, okay, you present your graph, and I just would like to ask, can we look to these pictures and see it like some complex, some
Simplicial complex, you mean?
yeah, or CW complex, and
CW complex, yeah.
and here the two cells of this complex, is it corresponds to some relations, for example, like pentagon relations or other? I mean,
in
here
this context, yes, they do correspond. And in this very context, they correspond. So the hexagon the standard hexagon in the middle is what is called the commutativity associativity constraint. So the specific, I mean, there is actually a specific equation for it. And where's the standard one? There. Let's see. If we go back, oh, this page, and I need to rotate it. View mode, orientation, rotate left. So this is the standard condition. So with the associativity, we go from this tensor product to this tensor product, then we apply commutativity, then we apply associativity. So this gives one possible composition of three morphisms, and then another way of reaching to the same tensor product. This diagram should be commutative. Now that commutativity condition, which is, we could say, is a constraint, algebraic or categorical constraint, is actually has a corresponding geometric intuition in the sense that I want to now see this as a two cell. And, you know, since I've started already going from 1 to 2, I could imagine going from 2 to 3 and so forth in, you know, arbitrary cases. And how would that occur? Well, when I increase the number of objects here, I'm going to get more complicated structures, and I want coherence on all those possible diagrams, and that's going to give higher dimensional cells. So that's also a direction that I would like to explore and delve into, and I'm going to leave it sort of towards the end of the discussion.
Okay.
Mm-hmm.
And I may ask one more last question.
Yes.
I look at the picture that you show us, and I have a very stupid question, but maybe is it related somehow to the Clifford algebra?
Oh, so basically, Vasily already had suggested that this is related to possibly octonions and quaternions. So if we could, this is sort of conjectural. If we could actually establish a connection to octonions, then obviously it would be related to Clifford algebras as well. But at the moment, the link is not, you know, at least in my mind, not something established, you know, in full detail, but it's also worth exploring. Any other questions?
Oh, no. Okay, thank you very much.
Okay, you're welcome. So, I mean, thank you for the questions. So let's see. Now, continuing, I want to now, so how do I read this shape? How do I read the possible hexagons? Well, there is the standard hexagon that is sort of in the middle and also on the outside. And there are various other such hexagons. So these are ones in which there is basically a associativity preceded and followed by a commutativity, and then followed by an associativity. So I call those standard hexagons or alternating hexagons. So they go like associativity, commutativity, associativity, commutativity, associativity, commutativity, when you go around them. But then there are also these what I call non-standard hexagons. And how would I obtain such a non-standard hexagon? Well, actually, in fact, I could glue two standard hexagons that share a sequence together. So, for example, you know, there is the standard hexagon 1B, 1A, 3A, 3B, 2A, 2B, the central hexagon. But then I could also go, 2B, 2A, 3B, 3A. So that's the same lower half. But then in the upper half, go from 3A to 6B, from 6B to 6A and back to 2B. That's another hexagon. Now they share this triple edge.
And what's the
Now,
definition of standard ones and non-standard ones?
The non-standard ones, I'm actually explaining it through the example. They don't go alternating. So if I now delete the central one, the shared one, I get another hexagon. 2B, 1B, 1A, 3A, 6B, 6A, 2B. Now,
and
if I
what
look
is
at
not
how the
alternating?
edges go, it's no longer alternating, because a commutativity is followed by, instead of an associativity, a commutativity again. You have two consecutive
Okay. Yeah.
So it's no longer alternating. So I call those the non-standard hexagons. And I listed all possibilities for them here. There is 8 standard hexagons and 12 non-standard hexagons. And basically, I mean, the way of how do we exhaust it? How do we know we have exhausted the list? Well, we consider, so basically, one of these shapes, so it cannot consist of only commutativity constraints, because the largest shape you get in a commutativity constraints followed by each other is a square, that appears as a twisted square in this diagram. But so then you have to have an associativity. Then you say, well, before an associativity, I cannot follow an associativity by an associativity. It's impossible, because that would be traversing an edge twice. There is only, if you look at each vertex, this is a trivalent, this is a graph in which each vertex has degree 3.
Okay. Excuse me. So I see. I see that we have a polytope, or maybe a two-dimensional complex, where generators correspond to edges and relations correspond to hexagons. And there are 2 types of hexagons. We should understand the corresponding groups when we take only standard or both standard and non-standard. And that's the question.
Yeah, that's correct. And now, also, I'm looking at the graph theoretic properties and then trying to deduce group theoretic properties from there. When I look at each vertex, there's only one associativity constraint. So in a hexagon, an associativity constraint must appear, and it must be preceded and followed by a commutativity constraint. So if I fix this edge, there are 2 possible commutativities preceding, 2 possible commutativities succeeding the associativity edge. That gives 4 different sequences. And then I continue tracing, ending at one of these, I could be followed by a commutativity that would give rise to 2 commutativities being followed, or I could continue with an associativity, in which case I would be tracing a standard hexagon or a alternating hexagon. So those are really the 2 possible options, and this list is actually exhausts all the possible shapes. And furthermore, by the gluing operation, these hexagons themselves, as you suggested, have a algebraic nature or relation. There's a way of operating with these hexagons and cycling among them. But instead of working at the algebraic structure already present in the diagram, what I want to do is consider the action of an external group on this graph and trace the orbits and reach at a conclusion from there instead. But that's also, what you recommend is just as well a good direction to go. So let me return back to the, where was it? Okay, this one, no.
Yes, by the way, there is a question on the chat from Malik Marikar.
Oh, okay. Where is the, there. I can't. Where is the? I should say chat, right? For some reason, I can't see the questions in the chat. Can you read the questions or?
Yes, I will read it. Oh yes, it's just a comment. Clifford algebra, non-commutativity, magic, Arthur Jaffe. So this is just a comment.
Okay, Clifford algebra and
Arthur
okay.
Jaffe and something magic.
Kurjafa.
Okay, let's Malik, you can write it later.
Okay. Yeah, please do. Yeah. Okay. So now, continuing on. So I mentioned the three types of edges, alternating hexagons. So there are 20 hexagons. Now, if I look at the action of S3 on that diagram, so S3 acts obviously by permutation on three objects. I fix the lexicographic letter order on the objects. That's my initial object, and a certain permutation is going to basically permute these things. And by that permutation, if I look at the hexagons, standard hexagons, I get two orbits, one of size 6 and one of size 2. If I look at the alternating hexagons, I get again an orbit of size 6 and an orbit of size 2. Sorry, this is the same thing on alternating hexagons. I meant to look at the outer non-alternating ones. But again, just this by itself is significant because I could now consider the possible extensions of S3 by Z2, and this gives two cohomology classes. And that should mean that I should have a non-trivial co-cycle element that I could create from cohomology theories. And now I actually create such a co-cycle in which basically this co-cycle is going to act on the commutativity edges, and it's going to take the inner ones to 0, and it's going to turn the inner commutativities to the identity morphism, and it's going to preserve the outer commutativities. So this has the interpretation of if you can continue. I want to focus only on the most external interaction, the one that is visible from the outside, and I don't want to look further deeper than that. So if I do that, and if I consider, what happens in the diagram, actually the co-cycle condition modulo 2 is preserved. So that is actually a non-trivial co-cycle element that actually gives rise to the notion of a parity, because this is taking only values 0 and 1 and preserving some of the commutativity constraints, the ones that are
Parity
on
of
the
what?
outside.
Excuse me, parity of what?
So this is parity. This is parity assigned to in the diagram the red and green, the commutativity constraints. So the edges.
Red and green edges, right?
Yes, exactly. And if you go, if you go around the hexagon, you're going to get, in the standard. I think in the standard hexagons, you still get a 0 if you go around the full circle. So it might be differentiating between those two, but at the moment it's only differentiating between the commutativities that act on the outside and the commutativities that act on the inside. And now, basically, I sort of inspired by your parity in virtual knots in this setting, what I want to do is, start with my diagram C or category C, and then create a virtual version of it in which all the commutativities are replaced under this parity. So if it's an inner commutativity, I replace it with the identity. I don't consider it. But if it's on the outside, I preserve it. And this creates a virtualization of my diagram.
Do you mean that you will have parity projection? Yeah. Great.
Yeah.
Well, it looks like the following. So if we have a category, then we will be able to create a new category and a projection from the old one to from the new one to the old one, right?
Yes, exactly. That's exactly the idea. And it preserves the tensor products. So this is working on braided categories. So then the other sort of thing that I did was basically ran some tests. Wrote some code and ran some tests on the possible counts of the objects in the graphs. So in our graph we had 12 vertices, 18 edges, and it was 3 regular. It had girth 4, and there were no triangles, and there were 3 4 cycles, the 3 squares with the red and green or red and orange edges, and the 8 alternating and 12 non-alternating, in total 20 hexagons. So then this is the permito-associahedron. So if I consider the general question of if I have a string of length n, what are the possible parentheses placements? The number of, if I want to count the number of parentheses placements, that corresponds to basically counting hierarchical trees of, with n leaves, right? And that the answer is Catalan numbers. And this has sort of like a nice recursive formula, and what they are could be actually computed. And the nice recursive formula is, let me just note it here in the remark. So basically, if I consider it, there's always going to be an outermost tensor product, right? And this is of length n, let's say, and this one is length k, and then this one is length n minus k. So the first k objects are grouped somehow, parenthesized, and the other n minus k objects are parenthesized. So then basically my Catalan numbers should actually satisfy the relation ck times c n minus k, as k runs from 1 to n minus 1. Now, this is sort of, I find this interesting. So there is the resemblance of this to Küneth formula. So somehow through, maybe topological combinatorics, it should be possible to interpret this combinatorial formula, which is on, parentheses placements or tree diagrams, counting possible tree diagrams or on parentheses placements. And maybe it could be related to some Küneth formula-like property in which we are considering, let's say the nth cohomology, but then it's actually at that the underlying space is formed from some tensor, some product. And because of that, I could dissect the original object into 2 parts and then compute the cohomologies on each separately, and and multiply them when the degrees add to n over all possible choices. So this is very Küneth-like, and Catalan numbers come up in this context. And now, when I go to permito-associahedron, this time, what I'm going to do is consider 4 sequences of 4 objects. Now, there is 4 factorial different permutations. And then, if I have a sequence of 4, well, I have the third Catalan. I called it the 4th, but in literature, it's called the third Catalan number. The number of parentheses placements on 4 objects is actually 5, coming from the pentagon that I just draw. These are all the possible parentheses placements. So in total, there are 120 vertices. And then if we count the edges, there are 300 edges. And this graph this time is 5 regular. So, and the 5 regularity comes from here. If I consider a single object, a sequence of length 4, and then I consider, the possible constraint relations emanating from each. So there is already 2 that comes from associativity. Because this is actually, so, let's look here. Here is my inner tensor, and this is my second tensor, and this is my third tensor. So there are 3 products, and associativity takes, so if I focus on the inner, that's going to give me one associativity. If I focus on the outer, it's going to give me another associativity, and that's the end of all possible associativities. Now, if I consider the commutativity, I could basically commute the inner ones. So I would get x, w, y, and z. I could commute this one. So I could write y tensor w, x, and z. Or I could commute the outer using the outermost products. So z, w, x, y. So that gives 3 edges corresponding to the commutativity. So this is where the degree 5 comes from in this permito-associahedron. But then note that my original diagram with the hexagons resides here. Because if I look at these triple, even this one, these are all obtained from diagrams containing WXY with Z appended to the end. So the old diagram will sit in this huge permito-associahedron, and whatever we analyzed with S3 is still applicable, but actually this time S4 is going to act there. And then because of the pentagon, there is also the action of D5 dihedral group on the symmetries of the pentagon arising from possible symmetries of this pentagon right here. So these 2 groups will be acting on the permito-associahedron, and we get an automorphism group of order 240, and this is the count of other 4 cycles, the squares, pentagons, and the hexagons. So there is actually 880 different hexagons apparently. And so this is already somewhat studied by Kapronov in 93, and then earlier, of course, there is, they were also called Stashev polytopes, I believe. Now, we could also get a double cover by duplicating the 120 vertices, creating 2 copies of the whole diagram. And then when we have an associativity or inner commutativity, I connect the edges of this with the same second index with both 0 and both 1. But to distinguish outer commutativities, the ones with different parity, I now create a different graph connecting the 0th level to the first level. Now this results in a graph that I'm going to give the name D4. And that has an automorphism group of order 96. So this is the so-called parity double cover related to this. Now, so we want to search for an algebraic model for this. And what I call G4, so we already discussed, has 120 vertices and is 5 regular. And it has an automorphism group of 240. And candidates of order A120 are, there is S5 and there is binary icosahedral group A5 direct product with C2, and then there could be others. So if we do a random search, using a computer algorithm, and if there is no mistake with the algorithm, if everything was computed correctly, it looks like, it turns out that this graph G4 is the Cayley graph of S5. And this is what the algorithm found as the possible generators for the Cayley graph. So this huge permito-associahedron is actually a Cayley graph for S5. Now, there is the left regular action of S5, and there is the inversion automorphism. So it sort of, looks like the dodecahedron and the icosahedron may become relevant here, but it's not, at least in my mind, completely clear how they will come up. But it looks like they should be somehow present in the picture. And it would be interesting to look at the possible subgroups and the symmetry properties of these groups and see them hidden in this shape somehow. And G4, so the extra factor 2 in automorphism corresponds to an inversion. And also, now I also mentioned, because we have permutations on 4 letters, S4 is acting on the permito-associator. Because we have a pentagon with its possible symmetries, the dihedral group on 5 vertices is also acting. So their cross product is acting. So then it should be possible to embed S5 into S4 cross D5 because of this situation. So then we should get an injective homomorphism. Now, we created this double cover, and the layers 0 and 1 should represent domain, could represent domain and codomain of these morphisms once we choose a certain direction on these morphisms. Associativity and inner commutativity live on same layers, they are self-inverse, whereas outer associativity live on opposite layers. Now, of course, these statements, I'm sort of making guesses here. These are more like, potential conjectures or things to investigate, not, stating them as completely proven facts. Because, we have this interesting picture, and now I want to actually interpret it properly. And this is, so the double layer is an interesting device, obviously, and we want to make some sense, both in the algebraic and geometric setting, what those layers will correspond to. And also, we could say that there is a flat Z2 bundle. The parity function is a one cocycle. Cocycle condition implies trivial holonomy around every cycle, which implies a flat bundle. So determined by the fundamental group of the graph, or of the space generated by the graph, we have a map morphism to Z2, and this corresponds to our parity projection on isomorphisms.
By the way, so the photography method suggests that instead of category, we should use the topic data. And Alina is actually working with me how data can replace whatever category and whatever else. So we should understand how this works at the level of data and at the level of pictures. So the whole theory of doubling the complex and Z2. And one more theory which may be interesting for Alina is that this reminds, so here we may get pictures and something related to Penner, because no, not Penner, Penrose, excuse me, Penrose.
Penrose, yes.
Because instead of tensors, we can get pictures. and that will be interesting.
Yeah, exactly. That's great idea. Как я сама не... Да, это очень круто.
Okay.
Okay. When you say data, I'm sort of, I'm coming through. I've been in both worlds, let's say, both, more geometric picture centered and also more algebraic and computational sides. So basically, one question that I have is, one sort of relaxation on the definition of a category is, what if composition wasn't associative? So is that something that you think about in your term data?
Not quite.
Okay, do you have something that corresponds to composition in data?
I hope so. Let's
We'll talk
discuss it
about
with
it.
Alina.
Okay.
Let's discuss it with Alina.
Okay, yes, that would be great. Okay, so now the Montero's map from the pure braids. So this part, I'm not, this is sort of reiterating what I heard or learned from you. There's the pure braid group and the pure virtual braid group, but this time a braid on n strands and virtual braid on n times n minus 1 strands. And the idea was we were considering pairs of braids and we were looking at the secants and the trisecants. So the interactions between the secants correspond to interactions between the the strands, and the trisecants correspond to interactions among the interactions, so to speak. And so how do we write the product of two virtual braid generators, and virtual strands are labeled by ordered pairs ij. So classical braid strands, ZIT, when three become collinear trisecant, write product of two virtual braid generators and virtual brands labeled by ordered pairs ij. And the number n times n minus 1 is the number of commutativity isomorphisms in tensor category with n objects, this time allowing all possible, permutations on them, not, sticking to one possible ordering and just looking there. So here I sort of see a potential relation between the two pictures. This is, for some reason, I think every slide is repeated twice or something, but sorry about that. Zero simplices correspond to strands. One simplices the virtual generators APQ from pairs of strands. And the two simplices are trisecants, corresponding to possibly hexagon relations. And the parity cocycle corresponds to one cocycle on this complex and the double cover associated flat bundle. So this is sort of, Alina was asking about simplicial interpretation. This is the potential simplicial interpretation.
And what is what do cocycle what do two cells correspond to?
Two simplices trisecants, or the hexagon relations. In my world, it was we had the hexagon and then the two the commutativity of that diagram corresponds to the two simplex. So,
yeah,
for example,
somehow there is some hierarchy in GNK, in all those GNK or all those complexes, when relators for the lower one give rise to generators for the upper one.
Yeah. So basically, because I mean, also earlier the coherence axioms guarantee, one of these two cells or two of them acts as the whole generator for everything. It ensures, guarantees coherence on all the diagrams. But it's still, I think, worthwhile to see how the chain of enforcing goes. And if somehow the whole structure was changed, would there be a sort of a new obstruction coming to the coherence being enforced to higher levels? So those are the sort of, I think,
Well,
questions worth.
usually if you have if you have a complex, well, you may have a
Mhm.
polytope, and the relations come from two faces, and somehow if you have a two complex, then relations or constraints come from two faces, but they are more or less the same. They are more or less homogeneous. So the idea of all
Mhm.
those groups G and K is that everywhere two cells or codimension two events are more or less the same, and more or less the relation in our group is universal. So we
Mhm.
have this relations of length 6, or relations of length 8, or relations of length 10 for
Mhm.
areas G and K. So more or less they are the same. They just are just got by permutations of indices. So somehow, if you understand relations for one polytope, like associahedron or permutahedron, then you will have the relation for the whole complex.
Mhm. Yeah, yeah.
Okay.
I mean, it is definitely the case because of coherence in this particular setting, and as long as we have a sort of enough of a symmetry in, as long as the objects in our category look more or less alike in nature, then yeah, one version is kind of the idea of a fundamental domain in, the fundamental domain being enough to describe what happens on the whole complex plane. Kind of like one picture is enough if there is enough of a homogeneity idea. And
Okay.
it would be wonderful to sort of reach a general enough statement of that observation, to sort of, write it down concretely so that in different settings, one doesn't have to, check it every time and repeat the same proof, if you know what I mean. There is,
Okay.
again, oh, now I see. Oh, the commutator. Oh, yeah. Malik's comment is actually, now I see the comment. It's nice. That's also nice. It would be wonderful to actually, I will also discuss this with Professor Kaufman, and what Malik's suggesting could actually provide some clues, because he talked about the commutator, and obviously the commutation in the tensor product could, resembles the commutator in quantum mechanics, and obviously tensor categories provide the basis for quantum field theory as well. So probably the connection you're saying has some relevance, but it would be good to, again, to let's see, to pinpoint it exactly. So it would be wonderful if we could do that. And thanks for the comment. Okay, let's get back. All right. So now coming to the second cohomology of S3 by Z2 and the hexagon orbits. So this we captured in the second cohomology a non-trivial class, and we actually constructed a candidate for this parity in this particular setting. And this is not this is so this whole picture cannot be something arbitrary. There must be something deeper behind it, and of the sort of guesses because of
Semih, I
the.
think after this talk, we should write a joint letter to Lou Kaufman, and maybe you
Uh-huh.
write, and maybe I write, and maybe we can send him mm, uh, a, recording of this video. It's very crucial and very important. Yes.
Yes, I agree. In fact, I am going to speak at TQ at the quantum topology seminar tomorrow, and I'm thinking of sharing this material and maybe other related material there.
Yes, by the way, let's put the information about quantum topology to our seminar friendship group. It's
Sure.
we are friends for a long time. Yeah.
Yeah. Okay, so the speculations, or the possible connections, there is octonions and G2 connection, root systems. So octonions is an 8-dimensional alternative. Well, there is, the number 8 appearing in the alternating hexagons. So maybe those correspond somehow there. And then the 12 non-alternating could correspond to G2 root system, and somehow these two systems could be joined. But this is pure speculation stage at the moment. And so the alternating hexagons measure alternative directions, non-alternating hexagons measure full non-associativity. So, and also, I mean, one possible generalization that I want to think about is, well, this shape, this diagram, permito-associahedron, is for enforcing these conditions, but I still want to be able to study structures that are not necessarily commutative or non-associative. And still the same shape and what happened, or shapes coming from this particular shape, would become relevant, because then we don't necessarily have the two cells and the gluing. So somehow the whole construction fails somewhere, and we should be able to measure the failure somehow using the devices generated from here. And then Professor Kaufman mentioned meanders. So a meander of order n is a simple closed curve crossing a line at two endpoints. So basically, he drew many shapes.
May I see the numbers? Meanders of 6 equals what?
Oh, hold on. Wait, why is it not opening up? Is it because it's minimized? Okay. Okay. Number of meanders on 6 points is 8. Number of meanders on 8 points is 42. So this I gather that the meander number is not a solved puzzle yet. So they can calculate it to certain degrees, but there is not even a recursive
just
formula.
ask DeepSeek.
Okay, let's do that. Is there currently no recursive formula or formula known about meanders? Let's see. So there is no single universal recursive closed formula, and finding one for the general case remains a famously open problem in combinatorics. However, there are some, partially known results. So that's the answer it is giving, and it is giving links to something. And general.
Great.
So
well, this is good for people to solve. Yeah, this is a nice puzzle for people to solve. That's really great. Yeah.
So there are, I guess, special cases in which there is a you know, again, it appears that if we have certain symmetric considerations, there is even relation to Lie algebras apparently. So, and then there are some sources.
Yes, and also meanders can be related to D diagrams with something on the top and something on the bottom, which I used to encode knots. And I think that Alina also likes such diagrams when we have something on the top and something on the bottom.
Exactly.
Yes.
When you
Yeah.
say something on the top and bottom, what
Well,
do
I
you
mean,
mean?
if we have a meander, then we have a curve above the line and a curve below the line.
Oh, yes,
So we
yes,
can
yes.
write something like pairs of brackets, and this is very much related to knots in various ways.
Mm-hmm.
May I ask, is it true that it's actually related to the bipartite graphs when we have two types of
I mean, I was thinking about that just before the presentation. So basically, here is the problem with these constraints. If I fix a direction on the morphism, it becomes a directed graph. Now, I can turn it, and then there is the story with the double cover. In each of those cases, if I create a double cover, I turn it somehow into a bipartite graph. And if I consider it as a directed graph, I can turn directed graphs into something like a bipartite graph by by making if I have a directed edge, I make the origin or the vertex with the second coordinate 0 if it's a source, and if it's a target of an arrow, then I make it that vertex comma 1. So then the 0 layer and the 1 layer, you have two copies of the original vertex set, but then you just have edges going from the 0 set to the 1 set, or to the set at level 0 to the set at level 1. Was that along the lines of what you were asking, or? Alina?
Yes, I'm here. I'm not sure, but anyway,
Uh-huh.
it was interesting. I just need a little bit more time to
Mm-hmm.
to get it, to catch this understanding. Okay,
Okay, yeah, sure, no problem.
great.
Okay, now let's see. Parity. Oh, where's the... Okay. So here's a possible conjecture. Maybe the number of alternating hexagons for n objects equals number of meanders with 2n intersections. And I'm not exactly sure if that's true at all or not, but I mean, obviously you remember kind of the thinking I was engaged in when I was considering the possible gluings among the hexagons. I would find common sequence of edges and then delete them. Now and there is sort of an analogous, I'm not going to say same, operation in creating a meander. So you take a meander and you delete a certain part, and then you enclose the part that you deleted, you enclose it as a loop from the outside. So there's a way of generating new meanders out of old ones, and there is a way of generating hexagons out of old hexagons, or some altered possibilities of different ways of going. So maybe because of that correspondence, there could be some link between the two, but again, it's a speculation or a conjecture. And then there is the dodecahedron and the Leech lattice. And these are, again, coincidences of numbers are hinting at maybe the Leech lattice, has, because it has a 20-dimensional sublattice in certain constructions, and because in a dodecahedron one could consider the symmetries of inscribed cubes inside the dodecahedron, and there is some number matching. It seems like there is some coincidence among these things.
You consider the five. You consider the dodecahedron with inscribed. There is five, exactly these 5 cubes.
Yeah.
Interesting.
So Alina, you may remember some pentacot and your nice pictures with one platonic solid inside the other one. So
yes, sure.
So yeah, I think those could be very much related, because again, in this diagram, sub-diagrams or sub-constraints could be corresponding to, other shapes embedded in the bigger shape. But again, I mean, I didn't actually work out the details yet. It would be nice to verify for certain, to reach for certain whether there is a connection and what the nature of the connection is. It appears at the moment that there is a very good chance that there's a connection. So future directions of where could this go? We could generalize to n greater than 4, compute alternating hexagons, and test whether there is some validity to meander conjecture, or if the conjecture is false, if there could be a potential link between the two computations. And then in terms of cohomology, if I now consider, instead of sequences of 4 or 3 or 4 items, I consider sequences of n items, and then I consider the orbit decomposition of hexagons under the action of the symmetric group on n letters, and how that is going to correspond to the second group cohomology of Sn with Z2 coefficients. So again, that would be the co-cycle condition, and the parity generalized to other cases. And is it going to be, again, the distinction between the inner and outer in this time? And furthermore, when we say inner and outer, that's sort of like differentiating only between two possible cases. But even the inner, when n becomes bigger, I could differentiate the inner among each other, because the commutation could occur at a depth k. So no commutation until depth k, but some after k or something. And that gives sort of like a possible, what's it called? Something like a, what flags are. So the way in flags, how objects of a certain dimension sit inside the objects of a one dimension higher, nested within each other, kind of like Matrushka dolls or something in some sense. So that's also the direction worth exploring. And then there is the octonionic tensor category with a 12-split, higher categories, 3 cocycles, invariance of 2 knots. When we get to higher categories, in terms of simplices, I'm thinking of higher simplices. So we consider the 2 cells. What would be the meaning of 3 cells in that case? And can we go higher? And then there is, using this approach, it could be possible to introduce Topos theory and compute the cohomology of En with Z2 coefficients. So this is sort of summarizing what we set so far? And then could there be application to quantum computation to anion types? And could we characterize the generating set of S5 as the KD graph of this graph? And could we identify double cover automorphism group order 96 with a known group? So that's so if we summarize what we did so far, we did looked at the full coherence graph for 3 objects which had 20 hexagons with 8 of them alternating, and we had the natural parity grading and a co-cycle condition and a parity projection functor, and we computationally verified for 3 and 4 objects that the 4 object graph is permito-associahedron, and the KD graph of S5 with inverse closed generating set appears as this graph. And we looked at some possible geometric interpretations, the coherence 5 cubes, and the embedding of S5 inside S4 cross D5. And we consider the double cover as a flat Z2 bundle, and Manturov's map as Manturov's map's geometric realization through this connection, and connections to cohomology, octonions, meanders, and Leech lattice.
Well, that's great. Please send us the slides and I will comment.
Okay, sure. Yeah. Okay. Thank you very much. And I wrote down some references, but not a lot. I mean, the thesis work is, the original action of the S3 on the diagram, etc., was at the time I had, slow connectivity with internet, so I had difficulty accessing many, sources. So it's mostly done on my own initially, but I'm trying to find its connection to the literature and find its significance, its position of this calculation further. So I would welcome any type of recommendation and how to further this work. Okay. And
okay. So it was an extremely interesting topic, and I enjoyed listening to it. So, dear friends, are there any comments or remarks? So please.
I think it would be very interesting to realize this talk in a sense of Penrose and his как сказать, подход.
Approach.
And his approach to tensor category when he preferred to make some pictures, but it was absolutely correctly. And I mean the his picture calculus. It's interesting to look at your work again and again, but in a sense, I mean, I think it would be interesting.
Do you have a particular article of Penrose or a book by Penrose that you have in mind?
Yes, I have an article. I know how to find it. Maybe actually I can just now find it. It's very quick. I can just put it on the chat.
Okay. Yeah, sure.
Okay. Well, I think we should organize a separate meeting with Alina and Semih. Yes, and any further questions, remarks, maybe? Yeah. So it was really a great talk. I really enjoyed it, and we have so many problems. So really, I appreciate this talk. Thank you very much.
You're welcome.
Mhm.